Hello everyone, my name is Marc Abboud and I will be talking about the paper that I wrote with Thomas Prest called the Cryptographic Divergence, New Techniques and New Applications. So most of this work was done while I was an intern at PQ Shield, the company where Thomas is currently working at. So there's going to be three parts in this talk. First, we're going to talk about divergence in security proofs. Why do we use them? We're going to compare statistical distance and Renyi divergence, and then we're going to talk about a new class of divergence that we introduced with Thomas in the paper that has some nice properties. Then we'll move on to two applications of divergence in security proofs. First one is the security for prime number generators, and the second one is for secret private fully homomorphic encryption scheme. Alright, so let's dive in. First, divergence in security proofs. So the general context is that you have some scheme S and an adversary A, and there is a bounded number of queries Q, and you want to achieve a level of security lambda. You have a real distribution P and an ideal distribution Q. The thing is, you know that under the ideal distribution Q, the adversary has a low probability of breaking the scheme. And you want to know that remains true when you move from Q to P. This is called a reduction in security proof. And if the number of bits of security that you lose, see here on the slide, is low, you see that the reduction is tight. So usually when you do security proof, the first tool that you can use is the statistical distance. So this is the definition, and the nice property that it has is that you have an additional inequality, meaning that if Q of E is low enough and the statistical distance is low enough, then P of E will be low. But since you want P of E to be lower than 2 to the minus lambda, this typically requires that the statistical distance is also lower than 2 to the minus lambda. And this can lead to some aggressive choice of parameters for your cryptographic schemes. This is why instead we use Renyi divergence. So this is the definitions for the Renyi divergence. So this is a way to measure difference between two distributions. It is not symmetric. It's not symmetrical. There's technical conditions for the support of a distribution. So the definition involves the ratio between P and Q. This is a continuous class of divergence with a real parameter alpha between 1 and infinity. And you see that when alpha is equal to 1, you get the exponential of the Kublak-Leibler divergence. So what are the properties of this divergence? Why do we use it in security proofs? Well, first there's a multiplicative type of inequality. You see that for an event E, P of E is lower than some product of Q of E times the divergence between the two distributions. So this is nice because if Q of E is low enough, then you only require the Renyi divergence to be constant to gain the security that you want. And the second nice property is that when you have independent distributions, the divergence of the product is the product of the divergence. And this means that the Renyi divergence behaves well when you talk about number of queries. So if you want to formalize this, we state a lemma in the paper, which is that if you have an adversary that wants to solve a search problem, and you know that under an ideal distribution Q, the adversary solves the problem with probability at most 2 to the minus lambda, then if the Renyi divergence over the lambda is lower than 1 plus 1 over the number of queries, then you get a tight reduction when you go from Q to the real distribution P. More precisely, you lose at most 3 bits of security. So in practice, when we use Renyi divergence for security proofs, we will ask for tightness, so we will require that the Renyi divergence is of the order of 1 plus 1 over the number of queries, and that alpha is equal to lambda. Now I want to emphasize that this only works for search problems. For decisional problems, this won't work as great, because the advantage in this case is of the form 1/2 plus epsilon with a really low epsilon. And if you just apply the inequality that we saw on the slide before here, for a decisional problem, it won't give you better result than the statistical distance. So from now on in this talk, and when we'll talk about the applications, we will talk about security for search problems. All right, so now it is also worth mentioning that when you talk about Renyi divergence, there is also entropy counterparts. So for a discrete distribution, you can define the alpha entropy or the Renyi entropy, which is defined like this. And common examples are when alpha is equal to 1, you get the Shannon entropy, H2 is the collision entropy, and H infinite is the min entropy. So that's it for Renyi divergence. And now I'm moving on to a new class of divergence that we introduced in the paper with Thomas. And we call it the relative error of order alpha. So it is also a continuous class of divergence with the real parameter alpha between 1 and infinity. The main difference with the Renyi divergence is that there is a -1 in the absolute value and the exponent is a bit different. And you see that when alpha is equal to 1, you get 2 times the statistical distance. And when alpha is equal to infinity, you get the standard relative error, hence the name relative error of order alpha. So you get the continuous link between the statistical distance and the relative error. Okay, but what are the properties of this divergence? Well, it behaves a lot like the Renyi divergence actually. You get the same kind of multiplicative inequality, and there's a strong link between the Renyi divergence and the relative error given by the Minkowski inequality. Okay, so what this means is that even when you find a bound on the relative error, you will still use a Renyi-based argument for its security proofs. So for tightness, we will also require that the relative error is the order of 1 over the number of queries, and that alpha is the order of lambda. Now I want to mention another inequality involving Renyi divergence and relative error that was shown by Thomas in a paper in 2017, and which shows that if you have two distributions, then their Renyi divergence can be bounded by a quantity that depends on alpha and on the square of the relative error. So actually, in some cases, you would only require that the relative error is of the order of 1 over the square root of the number of queries to achieve tightness in the proof security, in the reduction for the proof security. Alright, the question you might ask now is, then what's new with this new divergence? Because it behaves like the Renyi divergence. And even if we get some nice bounds on the relative error, we'll still use the Renyi divergence for security proofs. Well, what makes this divergence stand out is that it has an amplification property, which has no equivalent for the Renyi divergence. More precisely, in a paper of Duca and Stele in 2016, they showed an amplification property for the statistical distance. The idea is that if you have a random function and you can bound the statistical distance for any 2 points, then when you iterate this random function, you amplify the statistical distance. And what we show in the paper is that you have the same behavior with the relative error over the alpha. The only difference is that we need a technical condition on the support because we use relative error, but otherwise the end result is the same. You have first a bound on the relative error and you can amplify it by reiterating your random function. So this is really nice, and that's what we believe made this divergence stand out when compared to the Renyi divergence. And we'll see an application of that later. But now we move to first application of divergence in security proof, and that is security for prime number generators. So what I mean by security is that when you have to generate random prime numbers for a cryptographic scheme, you want to do it as randomly as possible. So naively, you would just randomly sample numbers and output it if it's prime, otherwise just repeat this process. But this is very costly in terms of times and randomness, because you will have to repeat a lot of time before you end up on a prime number. So you want to use a more effective generator, and that's what we're going to study two of them in what follows. So we're going to denote by U the uniform distribution over the prime numbers. And the first generator we're going to talk about is the priming generator. So this generator was introduced by Brandt and Damgaard in 1993. And so it works really easily. You just have a parameter x, and you want to output a prime number between x over 2 and x. What you do is just sample a number n, and you add 2 until you get a prime. So really easy. But if you do it like this, you won't get an output distribution that will be close to uniform. Because if you take the following situation, where you have three prime numbers, q prime, q, and p, and there are no prime between them, you can see that the probability that p is outputted is a lot higher than the probability that q is an output. Because whenever m falls between q and p, then p will be the output. But for q to be the output, you need m to fall exactly between q prime and q. So there's an imbalance, and you have to solve this in order to get a uniform random generator. So to do that, what they did in the paper is that they introduced a parameter s, which is c times log of x. And the idea is that same thing, you first sample a number and add 2 until you get a prime, but you do that at most s times. And if after those s steps you don't get a prime, just return failure or you start again. And this will actually be enough to act like a random generator. And this is important because this algorithm is used a lot in the industry because of its simplicity. So in the original paper, what they only showed is that under the prime R-tuple conjecture, which is the conjecture from number theory from Hardy and Littlewood, they showed that the entropy of their generator tends to the entropy of the uniform distribution when the parameter x tends to infinity. So that's a behavior that you want, but it's not enough to assess security. What we show in our paper is that actually the Renyi divergence between the output distribution of priming and the uniform distribution is asymptotically bounded by a constant that depends on C. And that's really nice, because now that you have a constant divergence, you can actually do tight security proofs, you can do tight reduction. Equivalently, this gives a lower bound on the entropy for any order alpha higher than 2. And this is also really important because there are two practical implications about this. First one is that you get security against collision attacks because the collision entropy is high enough. And if you have a constant number of calls, then if you have a scheme that is secure with the uniform generator, it will remain secure using priming instead. And what we mean here, again, we talk about search problems. So what we mean is that if you have a scheme and an attack, an adversary that solves a search problem in order to break your scheme, if this adversary can't break the scheme under the uniform generator, it can't break it when you use priming. Now I'm moving on to a second generator, the one from Pierre-Alain Fouque and Mehdi Tibouchi. So this generator is a bit more complex than priming. You have three parameters: x, which is the upper bound of the prime number you want to find; epsilon, which is a real number between 0 and 1; and q, which is a constant that is of the order of x to the 1 minus epsilon. So what you do is first you sample the number a co-prime to q, and then you're going to sample number t, and until the number p that has the form a plus tq is prime. So you're going to flip again a fraction of the bit of P. And so the randomness needed, the bits of randomness needed, is determined by epsilon. So actually you want epsilon to be as low as possible so that fewer randomness is needed. And in the original paper, they showed that the average entropy consumption is given by this formula, so it depends heavily on epsilon, and you want it to be as low as possible. Now, what they show in the original paper is that under a conjecture from number theory, the Friedlander-Granville-Montgomery conjecture, they showed that the statistical distance between their generator and the uniform one can be made arbitrarily small. And this is the bound they get. So it shows that asymptotically this generator is secure. What we showed in our paper is that the bound they found remains when you use the relative error. So that's really nice because you know that you need the statistical distance to be lower than 2 to the minus lambda for security proofs, but you only need the relative error to be lower than 1 over the number of queries. So you can actually use a lower value for epsilon. We did some computations, and so, as I said, for statistical distance, you need the quantity that bounds the statistical distance to be lower than 2 to the minus lambda, and this gives you epsilon to be asymptotically higher than 0.36, whereas when you use a Renyi-based argument with the relative error, you need a bound that is roughly 5 times lower, so fewer bits of randomness are needed. Now we move on to the last part of this talk, which is about circuit-private fully homomorphic encryption. And the title of this section is Putting Washing Machine in Eco Mode. I'm going to explain this title later. So the setting is that you have a client C and a server S, and the client has a message M and wants to know the result of the function f of n, which will be computed by the server. But you don't want the server to learn anything about m or f of m, so you just encrypt everything. And this is secure if the server doesn't learn anything about the message or the result. We want an additional property that the client does not learn anything from the circuit used by the server. And this is useful, for example, if you're a company and you have a private algorithm that your client use, and you don't want them to learn anything about the algorithm. So this is called circuit privacy, and you say that the scheme is circuit private if there is a way, given f of m and the public key, to create a ciphertext that will decrypt to f of m, such that the output distribution is statistically equivalent to the one from the circuit, the one used by the server. If you manage to do that, then there's no way for the client to learn anything from the circuit used by the server. So the question is, how do you create such an algorithm M? And what they did in their paper, you can today, they use sanitization of ciphertext. So what they did is they created a function called the washing machine, function wash, that will re-randomize the set of ciphertext, and such that for 2 different ciphertexts, the statistical distance is bounded by a constant delta. Then you just do k round of the washing machine and use the amplification property to gain the security that you want. But now we know that we can do this security analysis with the relative error instead of the statistical distance, because we also have the amplification property for the relative error over the alpha. So this will lead to fewer rounds of the washing machine, hence putting it in eco mode. So we're going to follow the same example they use in the original paper. We're going to talk about LWE-ciphertexts. So we're only going to work on the case of the encryption of 1 bit. So here Q is a prime number, S is the private key, mu is the bit you want to encrypt, and eta determines the size of the noise, E, for your ciphertext. So remember that in order to ensure that you decrypt the right bit, you have the noise has to be lower than Q over 4. Now, how does the washing machine work? We're going to have two sets of ciphertexts, one with the big noise and one with the low noise, and we're going to bounce back between the two of them. There's two sides of the function wash. The first part is the refresh function. That is only a bootstrapping process that reduces the noise of the ciphertext, and this is deterministic, and this won't inject randomness. And the second part, rerun, that will re-increase the size of the noise, and that will inject randomness. So I'm going to focus on rerun. So how do you define rerun? Well, suppose that in the public key you have some amount of encryption of the bit 0. So we call them rerandomizers. What you do is you take a ciphertext C, LWE-ciphertext, and you're going to add a random linear combination of the rerandomizers, and you're also going to add a noise F, which is sampled from a distribution of your own choice. Now what you can show is that actually the only leakage that comes from rerun depends only on the noise of C prime and on the noise of F. So this is the point where you need to analyze in order to do the security analysis. So the question is, how do you sample F with which distribution in order to minimize the number of calls to the washing machine? So in the original paper, what they did is that they used a uniform distribution with the parameter B. And so you want to ensure correctness, so this gives you a bound on the size of the noise. And you want to ensure security, so you want the statistical distance to be lower than 2 to the minus lambda over k, because remember, we're going to iterate this process k times. And this gives a number of calls to be the order of lambda. Now in our paper, what we did is that we instead use a Gaussian distribution of center 0 for the noise F. Why did we do that? Well, remember that we want to use amplification property for the relative error, and we need a technical condition on the support. What is nice with the Gaussian distribution is that any point has non-zero probability to appear, but you know that when you're far enough from the center, you basically will never appear, or with really, really low probability. So we again get two bounds. First one, you want to know it to not be too high so that you have correctness of decryption. And then to ensure security, we want the relative error to be lower than q to the minus 1 over 2k, because we're going to apply Thomas's inequality, so proposition 4, for our Renyi based security proof. And this leads to k being of the order of log of q. So in practice, with this procedure, divides the number of iterations, the number of calls to the washing machine, by lambda over log q. Since here we're talking about fully homomorphic encryption, so lambda is still 256, for example, but log of q can be really low because fully homomorphic encryption is heavy. So it can be about 32 or 64. So you gain you can divide by 2 or even by sometimes by an order of magnitude the number of iterations you have to do. And this is important because remember, the bootstrapping process is really heavy. Now remember that this is that here we talk about search problems. So this means that if an adversary wants to break circuit privacy using an attack that solves a search problem, this provides security against that. Alright, so thank you for listening to me. I'll be now waiting for your questions.